A little bit of review. I'm going to be doing a little bit of reviewing of what we just did, all the graphical stuff. I'm going to grab some problems from old exams, recent ones, of course, and show you the problems that we're able to do just by having a knowledge of the graphical and the numerical aspect of these things. So I got to go find them. And where did I put them? Yeah, that one. Yeah, we'll grab the one from spring. No, that's from fall. This is from fall 2016. The very first problem is sort of has a little bit of everything that we've done so far. Remember, we got several different types of limits that can happen, or at least the way they look on a graph. So I'm pulling my first problem from that test. Came in small. I got to make that bigger. I'm afraid if I make it bigger, it's going to mess up. Oh, I can see it's all right. All right, as you see, we have 10 blanks to fill in the various limits, left and right, and limits. So let's start with the first one. X goes to negative 3 pi over 2 from the left. So if you look to the left of that vertical asymptote, you can see the graph is shooting down to negative infinity. So that one's pretty easy. Now next, go to negative 3 halves pi from the right. On the right hand side, you see that that is also going downward towards negative infinity. And so that automatically means that the limit itself exists. As long as the limit, left and right limits are the same, that is the actual limit. All right, my next one up is x goes to negative 3 pi over 4 from the left. If you look and you follow it from the left, you can see it's heading to that hole whose y value is 2. Now do it from the right side. If you go from the right, the graph is also heading towards that hole, which has a y value of 2. So automatically the limit is 2. Now we move on to x going to negative 3 pi over 4. So from the left, you can see that the graph is heading up to the point that has a y value of 2. From the right, the graph is below now. That has a y value of negative 3. And so the limit does not exist because the left and right are different. And finally, the last thing is, what's the limit as x goes to infinity? You can see there's a horizontal asymptote there intending that the graph goes to that number, which is located at y equals negative 2. So that's one down. It'd be nice to know that if you're preparing for my exams, the first question is practically always just like that. Let me make this a little bigger because I didn't like how small that came in. We can even do some of these, calculating the following limits. And as I mentioned, I would require 3 decimal places of accuracy if you don't have to do it exactly. So, and the idea is to show you, I off the top of my head, I won't actually know what to do first. That's why I'm bringing these in and showing you some of the things that I do to convince myself what the limit is. So the first one, part A, we have the limit as x goes to 0 of 2x squared over sine squared of 35x. All right, be careful with all your parentheses and everything like that. Clear out your y1. I'm going to do just like I have all the other ones and put it in y1. 2x squared divided by. Now I'm going to make sure, because I have to square sine, that I put parentheses in here. I think, in fact, that's one's fine, because sine will have its own parentheses. I'll put a 35x inside of the sine. Finish the parenthesis. And then another parenthesis to finish the initial one and square that whole thing. So let's, as normal, do zoom 6. And let's see what this graph gives us. You can see it's working. This one must be tough. Yow. That does not look like anything that I've ever seen before. Well, let's go into the tables. Now I want to put in small numbers, so numbers around 0. So let's see here. 0.01. Oh, 0.05. Okay, that's fine. And I'll increment by 0.01. All right, now let's take a look at the table values. I got 0.00516. If I go, let's go back 0.04, 0.0033, 0239, 0193. They're kind of doing something, but I don't. There's an error. 0, of course. 0.0017. I don't feel comfortable about this level of accuracy. I'm gonna squeeze a little more out of that table. What's this little thing? Oh, no, I don't want to do that. Unlock all the buttons. All right. Let's try 0.001 for my table start. 0.001 for the increment 2, fine. Let's take a look if I'm getting, now we're getting somewhere. Look at these numbers. 0.00163. See, these numbers, I can see these numbers are looking pretty good now because I went smaller. I had to increment even smaller than what I did before. I'm going to even do this more to really convince myself of this answer. Let's do 0.0001 for my table start. I think I'll do 0.00001 for my increment. Let's take a look at the table values. Now, I feel much better. 0.00163 is all I'm seeing for these numbers that are close to 0. Yeah, keep going up. 3e to the negative 5, 1e to the negative 5. Of course, there's an error at 0. But yeah, to 3 decimal places. I think I even have it to 4 decimal places. 0.0016 would be to 4, but I only require 3. So, 0.0016 rounds to 0.002. Let's grab that picture. That's my evidence. And look at the numbers as close to 0 as you can. That's where I'm going to draw my conclusion. I'm not going to write 0.00163. I'm going to write 0.002 because all it required was 3 decimal places. Let's move on to part B. The limit as x goes to negative 3 of negative 2x squared minus 3x plus 9. Yeah, what are you doing? I'm going to move this thing out of the way. Limit as x goes to negative 3, negative 2x squared minus 3x plus 9 all over 5x squared plus 14x minus 3. It's taken me a while to get in there. Make sure you put parentheses around both the numerator and the denominator. Don't forget to do that. That's almost always the errors that students make is they don't put enough parentheses. And the calculator, following the rules of the order of operations, will not know what you intend. Let's start with the Zoom 6 like I do anything else. Okay, so negative 3, it's just kind of flat looking. The graph is flat looking around negative 3. This tells me, I bet you this is a hole. So in order to uncover holes, we go down to the window settings, to the very bottom of the window settings. That's the delta x there. Pick a decimal that'll go evenly into 1. So 0.2. That's also close to what's already there. I see it. I don't know if you can see it, but we're gonna bring it in and zoom in. I see the hole there. All right, let's stretch it out. There it is, right under -3. Well, you could try, I guess, to use the graph. You can zoom in on a point and things like that, but I don't think it's as fast as changing these tables. So now I want numbers around. Oh, I got caught by the second monster again. I want numbers that are around -3. So let me start at -3. It'll give me an error there, of course. And I'll leave the table, the delta table, at 1e -5. Let's see what the table values are going to give me. I have an error, but look at those numbers. Now notice in the column it doesn't display all the decimals because it doesn't have the room to do it. But you can see these are very small numbers around -3. Let me look at these y values. 0.562499, error. 0.5625. I'm pretty convinced this is 0.5625. Technically, what I would write for the answer is 0.563 then. So I have more than enough evidence here to tell me what these values are. I think that I need go to the graph no more. I think you'll find the table a lot of times has the answer. Yeah, let's move that up. Stretch it out a little bit. And I'll circle in blue the area of interest. Those -0.5625s tells me the left and right limits are the same. So 0.5625, -0.5625. As I said, if you put 0.563, you'll be fine. I don't know why, but when I have a 5, I hate rounding one way or the other with it. Now the last one, part C. The limit as x goes to infinity? Let's try that again. The limit as x goes to infinity of 2 minus 3x divided by the square root of 1 plus x plus 2x squared. I don't need a parenthesis around the square root because the square root provides its own parenthesis. When you start plugging in the expression inside there, notice how the square root expands to allow you to put more in there. It's extending the vinculum so that you will be able to put in what you want and not have to worry about resizing it. All right, x goes to infinity. That's off to the right. It looks to me like the graph is leveling off there, and this wasn't a huge amount, but remember, infinity's huge. So I'm going to do like I did before, 9999 for my starting point, and I'll increment it by 10,000. Well, let's see what these numbers look like. Well, that's nice. -2.121. But look at those. Of course, those aren't massive numbers. I'm looking to see if the 3 is going to go up, and it looks like it might or might not. I don't know. I mean, these are big numbers, but nowhere near infinite in size, I suppose. So I feel pretty good about this answer, but I'm going to try to put in an absolutely monstrous number, like 10 to the 50th. Yeah. And we're going to store that in to x. Remember this routine? So I'm going to evaluate my function at x equals 10 to the 50th. So you go to the vars. If you want to know what y1 is, go to vars. Y vars. Function. Then choose y1. Enter. Too big. All right, fine. Let's get out of this. I'll just put in a smaller number, but still big in. I'll try 10 to the 25th power. It's got 25 zeros, so that feels pretty good. Come off the exponent, store that into x, store. X, enter. And then if you remember, vars, y vars, enter, enter. This time it worked. And there we are, negative 2.121. I feel pretty good about that now. I feel really good about it. So that's what my answer is, negative 2.121 to 3 decimal places, of course. Now, later on, we'll do these things algebraically as well, but I just wanted to see that as of right now, this represents 1/4 of the test that you'll be able to do just by visual and graphical evidence. And there's actually a couple more problems. I'll do that in the next example.